So cell potential, the electromotive force between these two half reactions, it is in many cases a representation of a spontaneous reaction. It doesn't have to be. Right? You can have a negative voltage, which just would be driving the backwards reaction. But we can talk about the cell potential pretty easy. We build our two half reactions appropriately, and then we connect them in some way via salt bridge and a wire, and we allow the electrons to flow. And so so what you can do is you can relate the cell potential to the delta G, to the spontaneity, to the Gibbs free energy. In fact, again, you can measure it for these reactions, and it's via this relationship. And so you can plug in the respective amounts. Again, when we balance our half reactions, we can use our number of electrons and this Faraday's constant, which is 96,500 coulombs per mole, which is a joule, joules per volt. Yeah, joules per volt, which is so it's a coulombs allows us to do this conversion, and out comes the unit of joules for our delta G. And so knowing the cell potential, we know the delta G for the reaction. Now, if this was under standard state conditions, we can figure that out as well. But you can also do it under non-standard state conditions, because delta G is equal to delta G naught plus RT ln Q. Well, you can plug in this relationship between voltage and Gibbs free energy into these equations, into our standard non-standard state condition. The Nernst equation is basically a way of calculating the cell potential under any condition beyond standard state. Right? E naught is under standard state conditions. This you can get right off the table. This assumes 1 molar, this assumes 1 atmosphere of pressure, right? But you can do it under any measurement. Right? So the E naught, though, would represent the standard state condition. E cell would represent what the cell potential would be under non-standard state conditions. Right? So the Nernst equation incorporates the negative NFE and the negative RT into a constant that shows up before this Q, reaction quotient. Again, the reaction quotient is the balanced chemical reaction. Comes from just like what we saw back in equilibrium. And so that equilibrium value is related to the equilibrium constant. That equilibrium expression is related to the equilibrium constant and how you set it up, which goes back to the balanced chemical equation, which you were able to determine before. All right, so that's where the Q comes in. Now this is a natural log, and it's kind of awkward, and so R is a constant, N is a constant. Faraday is a constant, and the temperature, if we run it close to room temperature, we can sub in the temperature, and so all of these constants can be combined. On top of that, you can do a little massaging with the natural log, and rather than put it in natural log, you could put it into log base 10, and you can then rewrite the Nernst equation as follows: that the cell potential is equal to the standard cell potential minus 0.059 divided by n, where n is the number of electrons, all right, times the log of the reaction quotient. Right? Very powerful, very flexible. I mean, you can, like I said, you can plug in almost any value, and what this allows you to do is look at how concentration affects cell potentials. All right, so these three equations allow us to interrelate Gibbs free energy, equilibrium constant, and cell potential. All right, so we know this one from our previous work, but now we can start to see the cell potential. Under equilibrium conditions, the cell potential, not the standard cell potential, but the cell potential, under equilibrium conditions, this cell potential drops to 0. Right? It's like under equilibrium conditions, the delta G drops to 0. So we can use that relationship to to pick what the equilibrium constant is for a particular reaction very easily by measuring the standard cell potential under standard state conditions and back calculating K. Right? So very powerful. Right? So let's use the Nernst equation. Let's look at a typical one. What is the expected voltage in a cell, copper and zinc, right, at room temperature under these conditions? So again, it's always written anode cathode, anode cathode. So this is our oxidation, zinc going to zinc plus 2 electrons. This is our reduction, copper plus 2 electron going to copper 0. So our balanced chemical reaction is going to be zinc plus copper plus 2 goes to copper plus zinc plus 2. Products, reactants. And the reason we did this is so that we can figure out N, the number of electrons, and the balanced chemical reaction. And the reason we care, and the reason we did this is for the balanced chemical reaction. Now, the reason is because Q is equal to products over reactants. Solids drop out, and so products in this case over reactants would be the zinc ion plus 2 concentration times the copper ions concentration. Again, all this is implied in our line notation. Right? So we have to figure out our line notation to get our half reactions and then our half reactions. All right, so anode, cathode, and the reactions are written as is. Right? Now that we have all that, we can use the Nernst equation. We see that the standard cell potential, E naught, is equal to 1.14. We know that from our previous example, but we could look it up. We could look at the zinc couple. We could look at the copper couple, and this is going to be the cathode. So we could use ECAT minus EOC and equals E cell, and you should get positive 1.14 volts, and we did that in a previous example. So that's under standard state conditions. But now we're dealing with non-standard state conditions. And so we can use the Nernst equation. E is equal to E naught minus 0.059 over N. In this case, N would be equal to 2. N is equal to 2. Log Q, concentration of the zinc over concentration of the copper. And so we plug in our values for the zinc, we plug in our values for the copper. You multiply all of this out. I get this value is equal to 0.301 times 0.059 divided by 2 equals 0.008, and so this total voltage is going to be about E is equal to 1.14, 1.13 volts. Okay, so slightly lower. Now, if this reaction had been a lot lower, 0.1 molar, this is like 1 to 10, this would now be about 1.01 volts. All right? So 1.10 volts. So the voltage will drop slowly as you increase the concentrations. So relatively straightforward calculation once you have the balanced chemical reaction. Right. So let's take a look at another one. So we have a copper and zinc system, a copper and silver system, right? Slightly different molarities. We have our copper at very low concentrations, 0.0024 molar, and we have our, so we have two reactions. We have our balanced chemical reactions, they're written. We can look at the self-potentials off the table and we see the following. So we have our copper going to copper plus 2, that's our oxidation. We have silver going to silver plus 1, that's our reduction. We can build our So let's, again, what's really nice about line notation is it's relatively quick. You can look at it and just go cathode, anode, and so we can say E cat minus E anode is equal to E cell. All right, and so we can look and see that the cathode negative minus this number would give us an E naught for the reaction is equal to 0.50 volts, a negative 0.5 volts. So under standard state conditions, this reaction would not go forward. And that reaction, when you write it out, so as written, it's anode, cathode. As written in this, it's anode, cathode, so silver plus going to silver, that's going to be a 1 electron reduction, and then the oxidation in this case would be copper going to copper plus 2 electrons, and so that's a 2 electron bond, so we're going to have to balance this. It's required 2 of these. And so our balanced chemical reaction will be Ag plus times 2 plus copper solid going to copper plus 2 plus 2 silver solids. And again, this is a 2 electron process, and so the other important tidbit here is Q. Once you know the reaction, Q then becomes products over reactants, copper plus 2 over silver plus squared. Now again, this is why knowing the balance reaction is important, especially when you have acids and bases in there. It gets crazy really quick. gets crazy there really quick. Right? So now we have everything we need to use the Nernst equation. So we put in our -0.50 volts. Again, this reaction is not spontaneous normally, but we're not looking about that's spontaneous under standard state conditions. It's going to give us a positive cell potential. So let's see. Minus 0.059 over 2, that's our number of electrons, log copper concentration. In this case, the copper concentration is 0.024 molar, divided by the copper concentration of 0.0048 molar squared. So I will combine all these into a final number, 0.024. So I get about 1,000 for this combined number. We'll take the log of that. The log of that is 3. 3.0 times 0.059 divided by 2. So I get negative 0.089 for this value, 0.50 volts, negative, and so I get total for the cell, E cell, is equal to negative 0. 0.0, oh my god, my brain, 0.41 volts, still negative, alright? So the potential raises a little, but doesn't quite trip over into the positive territory, right? So that's how I would determine the cell voltage. This reaction would still not be spontaneous, but there you go. Right? Now, what's nice is it works the other way too. You can plug in a voltage and measure concentrations of things at equilibrium. Right? It's really powerful. We're not going to cover that. We'll save that for another class, but it's very easy to do once you have those values. In fact, that's how pH meters effectively work. They measure the potential of a cell, and you can use it to relate to the concentration of acid in solution. All right. So that's the last major topic of electrochem. We could spend all day. You could spend a whole class on this. In fact, I'm pretty sure you spend a couple weeks on it in quantitative analysis. So there you go. Where electrochemistry gets interesting is that it works in reverse too. All right, galvanic cells are spontaneous, all right, and you can actually use them to drive electrical energy. But you can reverse the reaction as well. You can use what we call an electrolytic cell, one that's non-spontaneous. You can drive the reaction backwards by forcing electrons into the system. Right? And so a reaction like iron going to iron plus 2, that's spontaneous under standard conditions, you can put in a potential of negative 0.7 volts to pull the electrons off the iron and push them back into the iron 3, push it backwards. And so you can drive the reactions backwards.